Welcome to this explainer. I am absolutely thrilled you're here today because we are looking at one of the most mind-bending mysteries in our entire solar system. Have you ever looked up at the night sky and just wondered what secrets the gas giants are hiding? Well, today we are decoding a massive, perfectly geometric storm spinning right at the North Pole of Saturn. Let's get right into it.
Okay, I want you to picture this. Imagine a storm so incredibly vast that you could drop the entire planet Earth inside of it and it would still have room to spare. Now imagine that instead of being a messy swirl of clouds like a normal hurricane, this storm is a nearly perfect six-sided shape, a giant hexagon just spinning away on top of Saturn. How is that even possible in nature?
Okay, let's dive into this. Here is our roadmap for the investigation. We'll hit the Saturn hexagon mystery, triune harmonic dynamics explained, the phase-locking hypothesis, validating the THD model, hypothesis falsification parameters, and wrap up with real-world planetary implications.
Section 1. The Saturn Hexagon Mystery. Decades of Cosmic Curiosity.
So this cosmic cold case actually stretches all the way back to the Voyager missions in the 1980s. Now, traditional weather models try to explain pieces of this puzzle using rotating fluids and deep seasonal storms. But here's the glaring problem. They completely fail to explain why a perfect six-sided geometry persists across decades without breaking apart. I mean, in a chaotic gas giant, a storm shaped like this should just shred itself to pieces, right? But it doesn't. It persists even deep down into the atmosphere.
And to put that into perspective, look at this number, 300. The winds in this hexagonal jet stream are whipping around at roughly 300 miles per hour. Keeping a perfect geometric shape at those extreme speeds is just wild. It absolutely requires some kind of hidden structural framework holding the whole thing together. It's not just a random cloud formation, it is a highly organized system.
Section 2. Triune harmonic dynamics explained. The universal pattern. To solve this decades-old planetary puzzle, we need a completely new lens. So what exactly is triune harmonic dynamics? Well, THD is a testable framework proposing that all change follows a repeating 3-6-9 mathematical rhythm. That's emergence, tension, and resolution. Think of it like the natural gears of the universe, whether you're looking at tiny spinning particles or giant evolving planets. THD suggests that energy and matter naturally organize themselves using this exact same predictable rhythm.
And this groundbreaking framework comes directly from Kevin L. Brown, who is a brilliant researcher, inventor, and author. His work on triune harmonic dynamics forms the absolute foundation of the hypothesis we're looking at today. As Brown states so perfectly, the universe evolves in harmony, and that harmony speaks the language of three.
Let's break down this 3-6-9 cycle so it's super easy to picture. Imagine you're on a crowded highway. Step 1 is emergence, that's number 3. That's when cars first start merging onto the road, creating a flow. Step 2 is contrast, number 6. Traffic gets really heavy, cars are switching speeds, tension builds up. It's kind of chaotic. Finally, step 3 is integration, number 9. The cars naturally organize into distinct fast and slow lanes, so everyone can keep moving smoothly. A stable, higher level of order is reached. That is the 3-6-9 rhythm in action.
Section 3. The phase-locking hypothesis. Saturn's wave number 6 storm.
So the crucial point is applying Kevin L. Brown's THD framework directly to Saturn's North Pole. The core hypothesis is that Saturn's polar jet stream gathers so much extreme rotational pressure and wind shear that it eventually crosses a critical threshold. When it hits that breaking point, instead of turning into pure chaos, it literally locks into a stable, six-sided pattern known as a wave number 6 standing wave. The hexagon isn't just a random shape at all, it's a phase-locked pressure release, perfectly matching the integration phase of THD.
But what's actually building up all this pressure? Well, think of it like a tightly wound spring just waiting to lock into place. The main ingredients, or structural pressure variables, include Saturn's crazy fast rotation, extreme wind shear where different bands of air are just scraping against each other, a really strong central vortex acting like an anchor right at the pole, and distinct layers of temperature in the atmosphere. All these forces squeeze together until snap, the six-sided shape locks right in.
Section 4. Validating the THD model. How science tests the theory.
Now, what's really interesting about this slide is that we can actually measure and predict the storm's stability. A theory is just a theory until you can test it, right? Notice the specific expected results here. If THD is correct, we expect the six-sided geometry to dominate over any random shapes. We also expect to measure very low volatility when the storm is safely locked into its phase. By tracking these specific wind instability and thermal metrics, scientists can predict exactly when that jet stream is going to stabilize into this shape.
And we actually see this kind of behavior elsewhere in the solar system. Take a look at Jupiter's Great Red Spot. It has stayed stable for centuries because of the surrounding wind shear and energy exchange holding it together. Or look right here at Earth's polar vortex, where cold air flows become dynamically trapped and self-reinforcing. Comparing Saturn to Jupiter and Earth really proves that rotating fluid systems locking into stable, long-term structures is a proven universal behavior. Saturn just happens to do it in the shape of a massive hexagon.
Section 5. Hypothesis falsification parameters. When does the model fail?
Now, good science is always about stating exactly how you could be proven wrong. And this brilliantly illustrates the strict failure conditions for this model. The hypothesis completely falls apart if observations show that the six-sided shape has absolutely nothing to do with the wind shear, or if it isn't linked to the strength of the central polar vortex. Also, if the shape is just some shallow cloud illusion completely disconnected from deeper temperatures, or if pressure builds up really high but no hexagon actually forms, then the THD model is wrong. It's a highly testable set of parameters.
To sum that up very simply for you, no pressure lock, no proof. If Saturn's atmosphere gathers all that rotational and shear pressure, hits the critical threshold, and a six-sided shape does not lock into place, the hypothesis is totally false. It really is that black and white.
Section 6. Real-world planetary implications. Beyond Saturn's weather.
Let's move to and see how this builds into practical applications. You might be wondering, why does solving a gas giant mystery millions of miles away actually matter to us? Well, by cracking the code on Saturn, scientists can translate planetary physics into real tools for Earth. It improves our atmospheric and climate modeling. It helps engineers design much better fluid simulations. It even helps meteorologists understand why the eye walls of massive hurricanes right here on Earth sometimes form into polygons. We're literally connecting a distant alien storm to extreme weather in our own backyard.
Ultimately, the major takeaway here is a massive shift in perspective. Thanks to Kevin L. Brown's THD model, we can stop looking at Saturn's North Pole as just an odd, freak storm. Instead, the question fundamentally shifts to, what universal conditions force a flowing jet into a locked geometric pattern? We are no longer just looking at weird weather, we are witnessing a universal law of physics in action.
Which leaves us with one final, incredible thought. If this underlying 369 harmonic law is powerful enough to shape a 20,000-mile-wide storm on Saturn, what else in our universe is secretly dancing to that exact same rhythm? Think about it. Thank you so much for exploring this with me today. Keep asking questions, and I'll see you next time.